Zoom is slow today. Since it's just loading anyway, I'm going to go check real quick and see if my son left his Zoom running before band downstairs or something. Oh, now it seems to be working. Okay, we are in week 9 of Math 105, and the homework last week was too hard. So I liked homework 8A. I think that was something you can just count things on the tables and be okay. But homework 8B was too hard. So what I'm going to do is move homework 8B to be 9A, and I will make a new one. So if you've already done homework 8B last week, if you're one of those few people, then you are ahead. You have done 9A, and you don't have to worry about whatever I put here. You might want to do it anyway, just to get feedback that yes, you're on top of things, but it will just be problems that look more like the practice final and be an easier thing, kind of the intermediate step before the hard ones here. Homework 9B I have started, but I haven't finished it yet. So there we go. That means if you go to our to-do lists and look at for week 9, week 8B, I haven't fixed it yet. So this still is that. And week 9A is exactly the same thing. It just has the new label of 9A. So to be clear again, the old 8B is the new 9A. If you've done it, great. I will try and go through in my records and give you the point in the grade book without you having to scold me. But if I miss it, just let me know. And you could be extra safe and send me a private thing in the Zoom chat right now saying, hey, I'm one of the people who did 8B, give me 9A for free. So I don't have to turn it in again. Okay, is that clear even though it's confusing?
David, will you still be accepting questions in this class for that homework, for the new 9A homework?
Yes, I will.
Okay, cool. I will wait.
Okay, we've done a bunch of homework questions already. So I want to point out that if you go to the week A, there's a Jamboard from this evening of Saturday study session that has some from 8A and some from 8B. And at least one of these I want to do again. There's also this page. Somebody Saturday night had this style of calculator with the PRB button. That is right there. And so we were figuring out how to use that button. That's what this is all about. If you don't own a Texas Instruments like this, then don't worry about that page. It is not for you. We also just did some homework problems earlier in today's Jamboard. So for part A, we did number 1 and 3 and 9 of part B, which is now homework 9A, and we did 3 from that also. But I'm happy to do more. I'm happy to repeat those now during class. And one of them I want to repeat for sure, just to sort of emphasize how powerful some of this stuff is and how you should not overthink it. So we have,
it was number, oh, sorry to interrupt. It was number 7, just whenever you're launching into that part of the class.
Old 8B, which is now the 9A.
Yes.
Okay. The flipping, okay. So I am thinking that maybe we should do 3 things today. One is we only have one topic left. If you go to our what's happening, then expected value is the only thing we haven't done yet. So maybe today we should just finish up the new material and know that all the rest of the term we're just reviewing, because we will have finished all the new topics. That might not be the right thing to do. We could save it for Wednesday, give you more time to do the things you've already seen. But if you just sort of want to check things off that, yes, there's no new stuff, now it's just studying, then we can do it. I also spent too much time going through data about false positives. We had homework problems that were, go back here, about positive and negative tests for, is my screen sharing? It's not telling me. There we go. Now it has the highlight. So we had the, do you have Lyme disease and false positives? So I thought we should do one with our actual Lane County COVID data. That's something probably that students want to see. Can we take this theory about how often do false negatives and false positives happen and apply it to the testing that we're actually seeing in the news? So that's a second thing to look at today. And then a third one would just be to go through homework questions. Start at homework 8, problem A, and see what questions people have. And if you repeat something that we did Saturday night or just now, that's okay. It won't hurt to see it again. So those are my 3 topics. Does anyone want to pick one to start with?
Can we do 5?
Do 5. You want to start with homework problems and start with 5 on homework A? Okay. Does anyone want one of the earlier ones before we jump to 5? Ashley in chat just said, can we go over it today? Which is the homework or the positive negative tests for COVID or the expected value?
The expanded, whatever you said it was, I'm sorry, the new topic.
The topic, expected value. Okay. I'm happy to do that, but let's save it for last if that's what people want. Number 3. Okay, so let me see if for 1 and 3, just showing what we did a moment ago at the study session helped. So for number 1, what's the probability the sum is 8 or more? We colored green all the ones that were 8 or more. There were 15 of them. For probability, you want the desired over the total. So we put it over 36. 6 times 6 is 36 for how many there are. And we got 42%. Odds is desired over the rest of them, the ones that aren't desired. So then we colored in all of these just to emphasize that those red ones are the not desired. And there's 21 of them, 36 minus the 15. And for odds, we normally write it as 15 to 21 or 15 colon 21. We don't change it into a percent. So we want the one that's 42 and 15 to 21. For 3, what percent of patients tested positive for Lyme disease? The table is incomplete. We need another column on the right side about what's the total number of people. So 19 and 10, there's 29 total people that tested positive. There's 1 in the 970 is 971 who tested negative. And if we add these two, then there's 1,000 people that were in the entire study. So again, the probability is the desired over the total. What's the percent that tested positive? It's 29 out of the whole 1,000. And this was potentially confusing because divided by 1,000, this step here, we're scooting the decimal point 3 times because we're dividing by 1,000. But this step, we're scooting the decimal point twice because that's how we always do decimals to percent. The fact that we just had 1,000 earlier in the problem doesn't change that when we go riplop, then we want to go right into percent. It's always 2, and we get about 3%. The final confusion was if you had a very old version of this, then there wasn't a 3% option. So I think it was a 2 with a typo. So I fixed it and put 2 and 3 on both of them. So if you need to reload your page to get all the bubbles, then do that. Somebody wants a turn with number 5. So sure, let's do that. I'm gonna shrink my window so I can grab. Anyone need number 4 before we jump to number 5? No one's calling for number 4. Okay, Mickey, be my director. Tell me what to do for number 5 here.
So I know that it's asking for out of the positive tests, what is the probability that the patients actually had Lyme disease? So what I did was I took the 19 patients that tested positive for the Lyme disease, which is so the 19, and I divided that by the 29, which is the 29 is comprised of the 19 positive plus the 10 false positives. So that combined is the 29. So 19 divided by 29 equals, I got 0.655, which if you do riplop, it's 66%. Sorry if I went too fast.
0.6. 0.655. Okay. I'm sorry, my fingers and ears aren't quite as fast as you are.
Yeah, sorry, I was getting a little carried away there. I just figure I gotta like word vomit it before my kid interrupts.
That works. Okay, ta-da. Anyone else have a question that they want help with on 8A or just a chance to show off with in 8A? Okay, the Saturday night we did one that I want to do again because we had Venn diagrams and I should have done some Venn diagrams in class. So we'll do them now. So a restaurant had a survey of which type of sandwiches people like and which type of beverages. And take that and make it transparent, copy it. Okay, there we go. I'm going to be too low. Keep doing it that way. Okay, so what's the probability that a customer prefers a peanut butter sandwich or they prefer coffee? So one thing you could do is not use a Venn diagram, and I will do that next. I will prepare my slide before I write all over this to say that if you don't like the Venn diagram, you don't have to use it because not everyone likes them. But I should show them more than I have, so let's do that. I have one blob, one oval, that's our peanut butter, and one that's coffee. What's the chance that they prefer one or the other? So we should look at the peanut butters. There's the peanut butters. And we should look at the coffee. There's the coffee. And if I want to translate my table into the Venn diagram, then I would say that there's also an overlap. So I would put that one of overlap with the one strange customer that liked coffee with a peanut butter sandwich. The other coffee people, 9 and 3, makes 12, and the other peanut butter, 14 and 2, makes 14. And then outside those two bubbles are the people that want neither peanut butter or coffee.
Peanut butter would be 16, wouldn't it? 14 plus the 2.
Oh, yes, yes. I think I even said 14 plus 2, but then didn't happen. Thank you for catching me. So what's the others? 9, 10, 11, 15, 22. So there's 22 other people that are not in any of those ovals. Everything okay with my Venn diagram now? So now my probability, as always, is desired over total. So I need to know how many people total are in my entire table if I add up every number. I could either add up all 9 of these numbers or add up all 4 of those. Somebody call it out. I know you've done this.
29 over 51.
Yeah, so there's 51 total. So we have I'm actually going to write a little more as a first step before I get to what Ashley had.
Now, I have a question about this one and 10. So when I did these ones on 8, I did it as the 29 divided by 51, which was 57%. But on 10, I had 29, but I had to remove 9 because the cheese and the coffee both had 9. So how come we didn't take one away on 8 with it overlapping?
We did because we didn't have this, the way we draw the Venn diagram, this one doesn't happen twice. The yellow is not repeated.
Oh, okay.
So if you didn't understand her question, that's exactly what I was about to do. Good segue. So I'm going to say, what happens if I'm not a Venn diagram kind of person? Then I can say, let's look at the totals. So how many are coffee? 13. How many are tea? 13. How many are hot chocolate? 25. How many are cheese? 7 and 9, 16. How many are meat? 18. How many are peanut butter? 17. Did I do all my mental math right? And a grand total of 51. Okay, I think everything adds up right. So what's the probability that someone prefers peanut butter or coffee? Then we could have the probability for peanut butter, and then also the probability that they pick coffee, but there might be some overlap. There is some overlap. So we have to subtract the overlap. That was the formula we saw last week. When you have the probability of peanut butter or coffee, you can add them up, but then you have to take away the overlap. So the peanut butter is this one, the 17 out of 51. The coffee is that one, the 13 out of 51. But then there's some overlap, that there is a peanut butter and a coffee. And we don't want to double count this person. Whoever picked peanut butter and coffee shouldn't get 2 votes. And we can color code it, that in the Venn diagram, this one here, oops, make it a highlighter. This was what was yellow before. The coffee we colored red, and it was 12 instead of 13, because we were being careful about the overlap before. The peanut butter was green. It was this number. And it was 16 instead of 17 because we separated out the overlap before adding things up. So either way, we have to be careful with the overlap. We either have to say it's its own thing. We shouldn't count it with the other peanut butter and coffee picks. We'll add it in separately. Or we should say, we're going to be haphazard and double count that person. But then when we're done, we have to remove them so they're not double counted anymore. Then we'll get to the same 29 over 51 that we did before. Oops. Is there somebody that likes the Venn diagram and wants to narrate me, give me directions for how to do it for a different one of homework 8A? Or is there someone that doesn't want to direct me, but just wants me to do a different one of 8A using the Venn diagrams? Or both ways.
I can give it a shot.
Okay, which one?
All right. I like the Venn diagram, and let's go ahead and do number 10, the probability that someone prefers a cheese sandwich or prefers tea.
Okay. Pardon me as I get everything set up.
Sure, sure.
Shrink it in. Oh, okay. Okay, don't rush me through this as quickly as I let Mickey rush me before, because
Okay.
it's sort of new material, not review. So let's go slow for people.
Okay. So in the first circle, it would be cheese,
Oh, okay.
and I would put the number 7.
And where do you get 7 from?
I get 7 from looking at the amount. Oh man, did I leave myself good notes? So let's see, the 3, so not 12 and 4, because the tea, so the question is cheese or tea, and 9 people prefer tea and cheese. And so I would put the 9 in the middle, and I would add the 3 and the 7.
So she put the 9 in there. That was the overlap.
Mm-hmm.
And there was left over in the blue area a 3 and a 4. And so that's where she got a 7. Everyone okay so far? Okay. I
Okay.
would actually want to label both circles as my very first step. That just makes my brain happy. Okay.
Sure. And then the remaining number of tea lovers is 4, which would be the 2 plus the 2 in the tea row.
Okay. So these two, the 2 and the 2, turn into 4 for the people that want tea but have not already been colored yellow.
So then I added 7 plus 9 plus 4.
Okay. There you go. So 7, 9, 4. Okay.
And that totals 20. Well, actually, to go in order, then I would put the total underneath. So that would be 51.
Because we still have we didn't actually label the ones that were neither cheese nor tea because we don't care. But if we did, just to be complete, how many would be outside in the floating area of the box?
31.
9, 1, 7, 14.
So now I will add 7 plus 9 plus 4, and that equals 20. And I would put that over 51, and then I would divide 20 by 51, and I would get 39%.
Okay. While we're looking at this, and just got a nice slow explanation, then I want to say, by the way, let's look at what the textbook chapter would do for this kind of thing. So they would have a formula of, where's their OR formula here? So they would say that the probability of this event or that one is one of them plus the other minus the overlap. Just the same as we did a couple slides ago, but written in a different way. So if you're looking at our formula page, because you are wanting to do a practice test soon or something, then I have put in our new official formula page our chart we had of all the different types of combinatorics, all the arrangements, and I put the book's version of all of these things. I didn't really have a good place on this formula page to say that what this is saying is the probability of one plus the probability of the other minus the overlap, the way I had translations for the book's versions otherwise. But if you want, I can try and squeeze it in. Since I've never tried printing this actually on an 8.5 by 11 paper, I don't want everything to be too tiny and not legible. As another question, as you can see, I made this one in a Google slide, thinking that that has already nice ways to print it, and you can resize it and stuff to make it how you want. If you want, I could save this instead as an image. If that's better for people, let me know. The old formula page was an image. Did we not have a link to it? I didn't. Guess we didn't have a link to it. So the old one is just an image, not a Google slide. So if that's better, let me know. I can do this. But I'm guessing the slide may be better. So that's what that is. I will label it for posterity. Okay, anything else about homework 8A? I want to emphasize that in real life, things will look more like this table than they will look like that formula. Right? No one is ever in real life going to give you two different probabilities and a third thing that's probability of their overlap. They're just going to give you a bunch of data. You're going to make a table out of it yourself, and maybe the Venn diagram, if that's what you like to. So, except on a math test, and maybe even never then, people just aren't going to give you these three items. That would be very strange. Okay. So the old week 8 part B, which is now the current homework for after class in week 9. Which of these do people want to have me do or show off that they can do?
I would like to add 9 to the list, so 7 and 9, please.
7 and 9? Oh, okay.
Yes, thank you.
4.
4,
5.
4 and 5. Okay.
Thank you.
There's a couple of these we did earlier. We talked about number 1. So let me go back to putting this. It doesn't have to be big. Okay. So for number 1, I don't think we actually wrote anything. We just talked about it. So let's actually write something. So if we have 3 appetizers, 11 entrees, and 4 desserts, maybe the appetizers are A, B, and C, and the entrees are 1, 2, 3, and like that. And the desserts are what, alpha, beta, or I don't know, what 3 letters should we use? X, Y, and Z. That may be easier than Greek letters for people that aren't mathy. Okay, so we want 3-course meals. We want something like A1X, right? That appetizer, that entree, and that dessert. Or C5Z, or something like that. That's what we're looking for. We have, in other words, 3 different boxes. And this one is for appetizers. This one is for entrees. And this one is for desserts. And we're putting one thing in each box. If this looks like license plates the way I wrote it, it's because it's exactly the same math as if they were license plates and not food. There's nothing here about taking a handful of things and how many different arrangements of those same things can you make? That would be a different problem. No one is saying, by the way, Marjorie is really hungry, comes to the restaurant and orders all 3 appetizers. How many different arrangements can we give her where there's no repetition? She's either eating the soup and then the nachos and then the fried foods, or the fried foods and then the soup and then the nachos, or whatever it is, right? We're not doing how many rearrangements of the same 3 things. She's picking one of these only, and so on. See the difference between the combinations and permutations? We're not rearranging things. We're just picking one and moving on. So how many ways can we pick something for the appetizers? There's 3. For the entrees, there's 11. And for the desserts, there are 4. And what do we do with the 3 and the 11 and the 4? Are we multiplying or adding? Anyone pick one and tell me why.
Well, I multiplied and that's just what made sense to me. I don't really have a bigger rational explanation for that.
Okay, that is right. You say it's right. And
So
also to write the number 132, just so we have a,
for every entree, for every 11 entree, we'll just take the first 2 to start. For every entree, we could have one kind of appetizer. And since we have 3 appetizers, then we do 3 times 11, because we have 3 different first choices that we could combine with our 11 different second choices.
right? If we were to list them all out, it would be in my code, A1, A2, A3, all the way down to A11. And then we'd have B1, B2.
Wouldn't A be just 3?
What?
Wouldn't A just have 3 options?
No, because we could put 11 different things with the A. So if we're only looking at this step, the appetizer and entree choice, I've just written all 33 of them. And then for all of those, I have to make 4 copies of my red grid, because I could put an
Okay,
X.
A is the appetizer.
A is that I could put an X after everything in my grid.
Choose.
I could put a Y after everything in my grid. Whoops, I have 4 desserts. I need like a W there. I could put a W after everything in my, right? So I need 4 copies of this once I get to the dessert step. So that's why we're having the 33 times 4. So if you have different pools of items and you are independently picking one from each, all you're doing is multiplying. And in the homework, you don't even have to actually find the answer. I just want to make sure you're clear that all we're doing is multiplying. There's no factorials anywhere in this. The factorials are about when Eli goes to the restaurant and orders all of the appetizers. How many ways can he do that? For number 2, I think we did this in the study session. No, we did number 3. How many ways can first, second, and third prizes be awarded in a contest with 175 contestants? So we go to our types of arrangements tables. Which one of these are we doing in number 2? Pardon me for making that too small, but that's okay. We are saying that we have things that order matters, because really you will be sad if you're in the contest and you get first prize, but they give you third prize, right? So the order matters, and we're only using 3 of the things. So we're in the n permute r land. And that's all the math you really have to do, because then you can just take your calculator and type in the secret function area, NPR, let me do it again, 175, comma 3, and it tells you the answer. If you know what's happening, you know that it's also 175 times 174 times 173. That gives you the same answer. But you don't even have to know that that's what NPR stands for. Which is one reason I gave you a homework that was too difficult last time, because they couldn't think of good intermediate things there. Okay, what next from 8B? People have called things out, but they have fled my brain.
4, please.
4, the local pizza shop is having a 5-topping special. So I will go back to get my chart again. This time I will look more carefully because we're not reviewing. So does the order matter?
No.
No, we're on the unordered side of the chart. Are we using all the available toppings? No, we're only using 5 of them. So we want n choose k, right?
David, if I may, so here's the question, here are the formulas. What were the indicators in the question that helped you decide what formula to use?
Because it doesn't matter what order my toppings are.
Okay,
It will come out.
it
the
would
same.
tell you
Yeah.
if it mattered.
You know, it's just sort of real life issues, right? For pizza toppings, the order doesn't matter. If you're getting first, second, and third prizes,
Then there's your order right there.
that
Okay,
order right there.
right.
If there's 3 raffle tickets that were all the same prizes, then order wouldn't matter.
Mm.
So it's just sort of pay attention. Right? We had one just before this where a pianist plays 5 pieces at a recital. And how many ways can the pianist arrange those pieces? Do we think order matters for that?
No,
Yes.
it does. Why? Because if she's got 5 And the question is just how many ways. Why does it matter what order it's in?
Because if she starts with her fast, happy one, or if she starts with her slow, somber one, those are different ways to perform.
Okay.
I'm sorry, that doesn't make sense. What does that have to do with how it's arranged?
How it's arranged, because arranging them 1, 2, 3, 4, 5 for this situation is a different effect than 5, 4, 3, 2, 1.
Well, but that's aesthetic though. That's not numerical. So I guess that question to me seems to have more nuance than the other. I get the example of the first prize, second prize, third prize, and the pizza toppings. Those are very clear and very different, and that makes sense to me. But this one seems to have more nuance. But maybe this is the trap of the word problem, right?
It could
Get caught up in your head.
Well, numerically, wouldn't it matter what way they're arranged because you can't repeat them like 5 different pieces? You have to play them like they wouldn't repeat. Wouldn't that, like, numerically, that's sort of a better answer to what you're looking for?
Table is things with no repetition. That's what makes it officially called an arrangement in combinatorics. The other reason we know number 2 has order not mattering is if order doesn't matter and you use all of them, this column, then there's only one way to do that. Right? If she's putting all 5 pieces in the program, and it doesn't matter what order she does that, then she's done, right? She just plays her 5 pieces. So since none of the answers are 1, then we know the order has to matter.
This one was just 5 exclamation point, 5 factorial, correct? Is use all items, complete permutation. So it was just an exclamation point.
Use
So,
all and
Yeah.
order matters. So that was the
Yeah.
Okay. Anyway, back to number 4. So we've picked this. So this is something that if I was saying it out loud, I would call it 14 choose 5. If I was to write it, I could write it as 14 choose 5, or I could write it as 14 choose 5, but I'm going to say it the same either way. And on my calculator, all I do is say 14 choose 5, and it gives me 2002. So is there knowledge of what's happening behind the scenes? Sure, I can look on this and I can say that I could just write 2002, right? Because my calculator did that and I believe it. If I wanted to do more, I could. I could say that this is 14 factorial divided by 14 minus 5 is 9 factorial, and then divide it by 5 factorial, and do the 14 times 13 and so on, and find what these things are. But I don't need to do any of that work. That's not what anyone is interested in seeing you do the long way.
Did you say divided by 5 or subtract 5?
That should be divided by. I'm sorry. So don't worry about doing it the long way. Have your calculator or the online calculator. Just use your special button. If it bugs you that we're skipping doing it the long way, I can certainly help you in a study session or one-on-one. There's some technique to it. I would take my 14 and I would actually write 14 over the 9 factorial, and then divided by the 5 factorial would be a times on the bottom. And when I start counting down, that's great. But eventually I'm going to get to 9. I'm going to write that in a different color. because that also shows up in the bottom. This 9 factorial here is also a 9 times an 8 times all the way down to 1. So those are going to cancel out because there's the same thing on the top and the bottom. And it's just a bunch of numbers multiplying in a fraction. And then I can do some other canceling and say, hey, right, this 5 and 2 is the same as that 10. This 4 and 3 is the same as that 12. So my answer is really nothing more than 14 times 13 times 11. There's a 1 on the bottom, but who cares?
No.
So it's not a terrible pain to do, but it's also like, why bother? We have calculators that do this. Okay, if you don't like this slide, that's okay. Again, the whole point is you don't need to do that. Okay, number 7. Shrink it so I can stick it on a board. Oops, no, not there. And number 9 people wanted. Did we have a request for 8? I don't remember. No. Okay, and 10 I definitely want to do. Okay, now I make this the right size. Okay, so we're getting things that are like heads, tails, 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 heads, heads, or something like that, right? That's what one of these stories looks like. We're flipping 2 coins and 3 consecutive rounds happen without any points happening. What did the actual one we care about look like?
I have a quick question. I know it's just a sample, but could it be heads, heads? Because I thought they each got a point if it landed on a heads for them.
Yes, one kid gets a point with the first coin heads, the other gets a point if the second one is heads. So the actual 3 rounds couldn't have had any heads. It has to be tails, 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 tails. So pretend this didn't happen because that was just a sample. So what's the chance when you're flipping coins to get double tails?
Isn't it just 50% because there's only 2 options?
Well, let's list all the it could have heads, heads. I could have tails, tails. I could have heads and tails. I could have tails and heads. Anything else?
Would those last 2 be counted as separate things?
Yep, because one kid gets a point with one. And
Oh, yeah, because it's 2 separate kids. Okay.
And even if they weren't keeping score, there's actually 2 separate things as far as how often they can happen.
Okay, so you have 4 potential outcomes.
I have 4 outcomes. So each of these is 1 out of 4.
Okay,
And they're coin flips, so they don't matter. So the chance of this happening and then that happening and then that happening, we're just multiplying. So not very likely.
got it. Thank you.
Where did the denominator, the 4, come from again? I'm sorry.
Because there's 4 different ways it could be. 1, 2, 3, 4. And only one of them was the one we're looking at.
Okay.
The way that I ended up doing this was for each of the T's, I calculated that was a 50% chance of each kid flipping a tails. And so I just did 1/2 times 1/2 3 times.
Yes, 1/2 times 1/2 would work to get the 1/4. That makes sense. Okay, for number 8 with these Venn diagrams, we did that right before class. Let me back up. So a hospital needs to hire people to be on call to provide language interpretation. And the numbers are not about the interpreters, they're about the patients. Which languages did the patients need? And an overlap was where a patient was bilingual. If you have French or Italian, you could help that one patient. If you did Hindi or Chinese, you could help that one patient. So what's the probability that one interpreter who is on call who speaks Spanish and Chinese, this person can help all the Chinese patients and all the Spanish speaking patients, will be sufficient for the next interpretation request? Pardon me for bad grammar, getting people's languages stating it sloppy. Anyway, so the desired over the total, the people that need Spanish or need Chinese interpretation. This bubble is 30 because we're including these 2. If you speak Spanish, you could help them. And this bubble is 7. We're including this one because if you speak Chinese, you could help this person. So that's the number of people that this one interpreter could help if they speak Spanish and Chinese. And the total, when I add up all the numbers, is 65.
So I thought in order for you to use a Venn diagram, they all had to be combined. So that was the biggest confusion to me. But this makes sense because you're just using your total and you're understanding who can do what.
I'm not sure what you mean by they all had to be combined. Is it that these 2?
I thought, yeah, because the Hindi and the Chinese was off to the side, I had a hard time. I thought that they all had to be circled together. So that's it. But it's good to know they don't have to. So you can look at these. The 2 circles off to the side, the Hindi and the Chinese are why. But why did you put them off to the side? Why didn't you combine them with the other ones?
I could overlap them. Let me see if I can physically do that on my screen right now.
I mean, if this is something that we're going to see.
Right, so I could draw them kind of, no, it doesn't get transparent. Anyway, there just wouldn't be anyone in the overlap, right? If I scooted these over a little bit, And I could have that curve here,
No.
wouldn't be anyone there. Just like there isn't anyone in this overlap. So artistically, you could scoot them around and make everything touch. Sure, there's just going to be empty overlaps.
Well, as long as I know that if I'm asked this question again, that they don't have to overlap in order to be, or not overlap. As long as they don't have to be joined, then that's fine. I guess it's the same thing as overlapping. I
When
was just,
you're drawing your own Venn diagrams, a
I
good
was overthinking it.
is this outside box.
Can I interrupt for a second?
Sure,
I missed the ending of 7. What was that again?
you missed the ending of 7. There. Okay, when I draw Venn diagrams, I like to put the box around. There's
Mhm.
usually people that are sort of floating around the outside of what we're actually caring about in that situation. And in this hospital one, the Venn diagram is artificially tidy, right? What hospital in the world would there be that only has people that need these languages and nothing else?
Hmm.
So it's probably like, oh, come on, let me adjust this. It probably is also like that. And then there's some people that are other languages. And the people that need, Vietnamese are over here and so on like that. So this is an unrealistically simple thing to be simpler. So I think part of the reason why you are bothered by the fact that they don't touch is there's no box around the outside. If you put the box around, now it's okay.
Yes, I have to think that simply.
So
Thank you.
put the box around the outside if that makes you happy. I just didn't want to do that because then people, when they're doing the homework, are going to say, well, what about all the Vietnamese speakers? Where is this hospital anyway? And so on. And that makes things too complicated. Okay, number 10. So I want to show you the power of all of this. And number 10 is a great example of that. A group of athletes consists of 12 people, 8 men and 4 women. What's the probability that a randomly selected team of 3 people could be all men or all women? So I'm starting with my most boring formula from this section. My probability is my desired ones over my total. And what ones do I care about? The all men teams. And I'm not going to write the word teams. I'm actually going to write arrangements to emphasize that's what we have. And also, I care about the all women arrangements. And my total is going to be the total arrangements. And this is an incredibly easy problem to make harder than it is. So looking at my chart up above, how many ways can I make a 3-person team that's all men when there's 8 men there?
Would be the choose button, so it would be like 8, choose 3.
Right, it doesn't matter in the team what order they are, whether we pick this guy first or that guy first, as long as they're in the group of 3. And we're only using 3 of them. So this is 8 choose 3. And realize that 8 choose 3 is just that there's these 8 guys and I'm picking 3 of them at a time. How many ways can I do that? Is David in the group or not? So on. It doesn't matter whether these 8 men or are standing in a field with 4 women, or on the top of Mount Everest all by themselves, or wandering about aimlessly. If I'm just saying how many ways can I pick 3 of those 8 men, with the order not mattering, it's 8 choose 3. So don't put the context in that there's 12 people and 4 of these people next to them are the women. That doesn't matter for this step. It's just there's 8 guys. How many ways can we pick 3 of them with the order not mattering? Okay, how many all women teams can we make?
Would be 4 choose 3.
Yeah, 4 choose 3, which I couldn't write that way. And then how many total teams can I make?
That's 12 times 3, which comes out to 36.
No, no. Think
No?
the same.
Okay.
I have 12 people standing around. At this point, I don't care that some are men and some are women. I just want to say, let's pick 3 of them, and that's one arrangement.
Choose 12, 3?
Yeah, so 12 choose 3. Everyone okay with my fraction now? So let's see what this is. We have 8 choose 3 is 56. There's 56 ways that we can make the men teams. 4 choose 3 is just 4. There's only 4 ways we can make the women's teams. And 12 choose 3 is 220. There's 220 total teams. So it's about 0.27, so 27%. So a great problem for combining the probability desired over total with the combinatorics of how many different ways can I make arrangements happen. Should I talk about why 4 choose 3 is 4? Why that makes sense? We have 4 women and we're picking 3 of them and order doesn't matter. So they're Marjorie, Mickey, Lacey, and Pamela. And what are the 4 teams? It's the team without Marjorie, the team without Mickey, the team without Lacey, and the team without Pamela. We've just listed all 4 of them. And more than that doesn't matter, because which order we do things, who cares? Trying to list all 56 ways to pick 3 guys out of 8, that would be a much bigger project.
So David, to explain it in my terms, so basically on the top, you've got 8 men. So the C is the possible combination, and then you've got 8 men. So 8 is the men, 3 is the possible, how many people per team, plus or women, and then 3 is how many people per team, divided by the total amount of people, comma, how many people you want per team.
Mhm.
Okay.
And if you keep wanting to multiply, instead of using n choose k, then just list the teams. When you get to the small ones that are easy to have your problem done, then say, what are those 4 teams? It's the Marjorie, Lacey, Pamela. It's the Marjorie, Lacey, and Katie. It's the Marjorie, Katie, and Pamela. And it's the Katie, Lacey, and Pamela. Those are my 4 teams. We are not doing the something with this many appetizers and this many, where did we go? We're not doing something like this, like license plates. We're not saying that we, for the first spot, have 4 choices, and then 3 choices, and then 2 choices, and then 1 choices. Because we're only using a few of the things, and order doesn't matter. Okay, onward. Let's actually finish up our topics by talking about expected value. There's types of change, but I'm going to save that for next time. It's kind of what we've done already, just being more careful. I will make this bigger. Okay, so we're talking about weighted averages. Let me grab that and put it on my Jamboard. So the weighted average of a group of situations measures the average result of a group. To find a weighted average, we use a table. Each possible outcome is a row, and then we work across with multiplication, and then we add things up at the end. And that makes no sense when I just say it out loud. So let's actually watch it happen. Was I nice to myself and I made a table? Yes. So I make a table. I have the sum of 2 dice, and I have all the different ways that I can have a result happen. Each possible outcome is its own row. Everyone okay with that part of the table? To be a weighted average, I need some value. So like 2, 3, 4, that's what the sum of the 2 dice are. And then what's the chance this happens? So I'm going back to my dice table, wherever that was. Here, dice table. There we go. And I counted on my little dice table and saw how many times I could get each thing. For a 2, there was only 1 way. For a 3, there were 2 ways, and so on down the table. So the new thing is when I have this kind of table, where all the different things are represented, they all have some number that goes with them, and they all have a probability that it happens, then I'm going to take each row and I multiply across. So for here, I get 2 over 36. This is going to be really hard to do unless I make it bigger. Can I make it bigger? No, Okay, I just have to make this bigger. For this one, 3 times 2 over 36 would be 6 over 36. 4 times 3 over 36 would be 12 over 36. 5 times 4 is 20 over 36. 6 times 5 is 30 over 36. 7 times 6 is 42 over 36. 8 times 5 is 40 over 36. 9 times 4 is 36 over 36. 10 times 3 is 30 out of 36. 11 times 2 is 22 out of 36. And 12 times 1 is 12 out of 36. Notice these products get bigger from 2 different reasons. Either the value was bigger or the chance it happened was bigger. So the biggest one is sort of, well, they're both reasonably big. But for the 1 out of 36s, the 12 counts more. It's a bigger value. The 2 is this tiny little one over here. And then when we're done, we take the average, the mean. We add them all up and divide by how many. So add this all up. 2 plus 6 plus 12 plus 20 plus 30 plus 42 plus 40 plus 36 plus 30 plus 22 plus 12 gives me 252. Then we divide it by how many? Oh, 1, 2, 3, 4, 5, 6, 7, 8, 9, 11. Wait, no, we got 250. I'm sorry, we don't divide by how many. I'm saying this wrong. We just are done. So that's 7. Getting ahead of myself too much. I'm getting it wrong. So add up the product, and then we're done. So all of this work just showed that the average when rolling 2 dice was 7, which you probably thought was true already. Let's do a slightly more interesting example. So here is one that people care about all the time in college. We again have different outcomes. And this is from someone's syllabus, not our class, of course. And this might seem like it's a different kind of doing this, and it is, because before, only one of these could happen at a time. You either rolled a 5 or you rolled a 7, but you can't roll 2 at the same time. But this student has attendance and homework and the midterms and the final. They have all of these. But it's still true that these are the different outcomes. And we've given each a number. And it's actually going to help because both of these are percentages. If for now we imagine that the first thing is just a plain number. So I'm going to cover up the percent symbols. Otherwise, having them there will confuse you. When you do expected value, the answer has the same units as whatever your second column was. So in the first one, our answer had a value of number rolled, because that's what we had. In the second one, our answer will have a value of score. And then we have a percent, and this isn't a percent chance that it happens, it's a percent of their grade it's worth. But the same game happens. So we have the product. We find the products and then we add them all up and we stop. So 90 times 10% is 9. 80 times 20%, 8 times 0.2 is going to be 16. 82 times 20% is going to be 16.4. 84 times 20% is going to be 16.8. 79 times 30% is going to be 23.7. And if I add all those up, I get 81.9. So the student's overall score is 81.9. And just like before, there were two ways that these numbers got bigger. Either they were bigger numbers or they were worth a bigger amount. Ready for another example?
Sure.
Okay, I'm going to steal one from my Math 25 homework. Let me shrink that better so it fits. Your friend is starting a food cart business. She's read that new food carts have a 35% chance to go out of business during the first year with a $10,000 loss, or a 30% chance to earn $20,000 profit, and so on and so forth. Assuming that the numbers are true, and that your friend is a completely random person with skill and luck in their new business, then what's the expected value for her first year's food cart business? So I need to make that table. What do I start with?
The dollar amounts.
That's going to be the second. So that's the value column. What do I label my first column?
Is it item?
Item.
What is it that we're?
Could do item. I think I like something better like outcomes or results or something like that better. Anyone have a preference for what word we put here?
Income,
Income, that's more like the value.
that's the value,
Profit is what they use.
Profit could be what
would be
value?
the value. So are you looking maybe for the percent of the chance, the percentage?
And the third
outcome.
one is always the percent.
Yep.
So we have go out of business as one outcome. And that's a minus 10,000 and 0.35. We could have small profit. For a positive 20,000. And that was 0.3. Everyone with me as I'm reading these?
Mhm.
We could have a medium profit. And that's a 30,000 and a 0.15. Does it help for me to make these a 0.3 and 0.15? We could have a bigger profit, which is 40,000. And that's also 0.15. And we could have the biggest profit, which is 50,000, but only 0.05. Everyone okay with turning my paragraph into a table?
Yes, that makes sense.
Okay, so now I am going to, for all of these, multiply. So this one would be a negative 3,500. This would be a positive 6,000. Double check my mental math here. This would be 4,500 if I'm thinking right. 6,000 and 2,500. Anyone getting different products than my tired brain?
No, I'm getting those same product numbers.
And we add that. And 15,500. So overall, you might make a lot of money your first year with a food cart, but that's not very likely. If you are a completely random person with no especially good or bad skill or luck in that business, then what we would expect is a 15,500 gain. Not a lot for your annual income. Assuming these numbers are true. Somebody could have just made them up. So expected values, which are also called weighted averages, happen all the time. If you are a farmer, you don't care what the chance of rain is today. You care the expected value of the rain. All the different categories, a little rain, medium, a lot, the chance each of them would happen, how many inches of rain that would be, and then you could know how to program your irrigation. If you are a traffic designer, then to some extent, the worst is what you have to handle. If it's rush hour, you don't want the roads to turn into nightmares. But if you can't do that, if there's just not enough lanes possible in the middle of someplace, too many buildings already there, then you can care about the expected value. On average, let's maximize how many cars are getting where they want to go. Maybe you're waiting at the airport and your types of categories are how long a wait it is before your flight finally takes off. And the values are less than 5 minutes, 10 to 20, 20 to 30, something like that. Those are the categories. You need to put a value on them. Is this how much money you're going to spend at the food court? Is this how many books you're going to have to keep with you? How many toddler snacks you need to pack? And then the percentage for which, how often they happen. So the airlines study this kind of thing to try and keep their customers happy in the waiting areas. So lots of applications for expected value. But because the math is a little tricky, then it tends to be something just done in business applications. You're not going to find an expected value for the weather report on the Weather Channel, even if that's actually more useful information than just, will it rain? Yes or no? What do you think? If we look at our test, then the random exercise that people care about looks a little bit trickier. And I'm just going to sort of narrate through this, but not give it away yet. We can certainly do a problem of this style next class. I would think it's strange if we didn't. So there will be something on your final exam that looks like this. Where we don't know their score on the final yet. This is a traditionally graded class. It has all of these different categories. We just did a problem like this, and we know that we want to multiply across and make a sum of the products. And some of these we can do. So 92 times 0.14 would be 12.88. But the last step, I don't know what to multiply by. The student hasn't taken the final yet. Instead, we know that these four products that whole section there and then if we also, let me actually not include that box. We want the whole thing here, including this, to sum to 75, because it says she wants 75% in the class in the problem. So you're going to get a bunch of them that you know and say, what else do I need to get to 75? And then once you have that number, you can work backwards and find out what she needs to get on the final. I'm going to get rid of D because that's going to. So that's enough to get you started. And that will test if you really understand absolute value or expected values well. And also this is one that happens all the time in colleges. But for today, if you can go forward, if you can just multiply across in each row and then add them up, good enough. I will put some simple ones like this on the homework 9B. Okay, we skipped over a little thing about the relative change versus absolute change. We've actually talked about this before. And before I go into those problems, I want to talk about the false positive data. Is the answer that? I don't know. Let's look and see since I didn't reload. Then yes, it was 71%. Okay, where am I looking? I'm looking here. So there was a website that was talking about false positives for the COVID-19 PCR tests. And they thought, well, we did false positives in an example problem with pregnancy tests and in a homework problem with Lyme disease. Since we're in the middle of a pandemic, then we should probably talk about it for COVID-19. And I want to not get into tangents about politics or what decisions you should make in actual life. I just want to go from purely the math perspective. And the math perspective is kind of uncaring and cruel. It's just that as someone that's looking at math, when the disease is very rare, then that makes it hard to look at the math. And let's see why. So I'm getting some information from this page. Anyway, if we have a population, this is just a theory, a practice problem. Make sure we're good at this. That has 100,000 people. And let's say that the infection rate was just 1%, 0.01. So I could say how many people were infected? 0.01 times 100,000. There'd be 1,000 people infected. How many people are not infected? I'm going to take the 100,000, subtract the infected, and get that number. Everyone okay with these two? So for COVID-19 testing, you can read here and you can read other websites, the false negative rate is about 25%. It might be about 20% depending on which studies you trust. And that shouldn't surprise you. Remember that the false negative rates for pregnancy tests and Lyme disease were higher also. When you're designing a medical test, then you really want to avoid false positives. And if that test unavoidably has a higher false negative rate, you just live with it. The false positive rate is pretty low, like 0.5%, 0.005. So not 0.05, which would be 5%, but 0.005, so 0.5%. So let's figure out what numbers go here. If I am infected, what's the chance I will get a false negative? I'm going to multiply these two, right? 25% of here. So that as I am infected and I'm accidentally testing negative, this one times that one. If I'm infected and testing positive, that's going to be everyone else, the 1,000 minus that. If I'm not infected, what's the chance I test positive? That would be the not infected people multiplied by your false positive rate. And the test negative rate is going to be everyone else, these not infected people minus the ones that had the false positives. And I'm going to double check that I didn't mess up. Okay. Everyone okay with this table now? So what's the percentage chance that a negative result is wrong? That would be the negative results that were specifically, I actually was infected. So that 250 divided by all of the negative results. So I get just a fraction of a percent, 0.25%. So even though the chance that any single test is a false negative is a quarter, a surprisingly big number if you didn't know these things, because there are so few people infected, the chance that a specifically negative result is wrong is less than 1%. Because most people that get a negative result are not infected and it's the right result. What's the chance a positive result is wrong? That would be testing positive and not infected divided by the total number of positives. So almost 40%. Even though the test is amazingly accurate, only 0.5% are false positives. there are so few people that were actually infected that most of the positives are false positives. If you have a positive result, some of those are actually infected. Most of them are, but there's also a whole bunch that are just false positives because there were so many people that were negatives to get a false positive off of. So it's how these numbers compare to those numbers that surprise people. That even though the false negative rate is high, very few tests are incorrect negatives. And even though the false positive rate is low, a whole lot of tests are false positives when a disease has a low infection rate. Questions about our theoretical example before we look at Lane County? Okay, so you can look at the data, right? I would be surprised if you haven't been to the Lane County website to see this stuff before, but there's currently a little more than 10,000 cases, cumulative, and 177 active in our county. So great news. That number used to be a lot bigger in older weeks, but recently the number of active cases has gone down a lot. Lane County's population is about 382,000. So if I do this number divided by that number, our infection rate is tiny. It's not 1%. It's not a 0.4%. It's about 4 or 0.05%. Right? So that's going to be bad news for accurate testing. The smaller your infection rate, then the more the false positives will happen, just because there's so many more people that are not infected. So here's Lane County. There's 177 infected, and we did a subtraction. Everyone else is not infected. So same process as before. How many people are infected but test negative? So that would be the false negative rate multiplied by the infected people. And then how many people had an accurate test when they're infected? That would be the rest of them. So 177 minus that. How many people were not infected but got a false positive? That would be this very small false positive rate times this large group of people. And then everyone else is the negative. Everyone okay so far? What's the percent chance that a negative result is wrong? So of all these negative results, the wrong ones are that. So very tiny. If you pick a random person that has no reason to think that they're sick in Lane County, and these are random people, right? So if you and everyone in your family had symptoms, this is not talking about that because that's not random. This is just picking a random person. The chance their negative result is wrong is tiny. Even though the false negative rate is high, the chance you actually picked a sick person to have a problem is tiny and cancels that out, overshadows that. The chance that a positive result is wrong, that would be that number, the test positive, but it says that you're actually not infected, divided by the positives. So almost everyone that gets a positive result in Lane County is wrong, which is why mathematicians aren't rushing out to get tested. When you have a tiny infection rate, then your test just isn't going to be accurate to catch them right. You can follow in that same link over here in the testing status and see that last week we had 10,711 tests, of which 220 were positive. So if I multiply those by these things, then the accurate tests were 14, but probably 206 were false positives, and so on. So it is really hard to get good data when the disease is rare. So great news in real life for Lane County that we're controlling this so well. But as far as trying to get good data, as far as trying to model the disease, then it's just not working well. We don't have enough sick people to count them accurately. It's a bit of a chicken and egg. How do you know how many current cases there are if your testing is inaccurate? And how do you get accurate testing if there's so few cases? If the test was 10 times as accurate, what if we change this 0.005 so that it has another 0 in it? It still doesn't change the numbers much. Now this goes down to 58 instead of 93. But it's still true that if you test positive, that doesn't tell you much. You would have to make the test 100 times better, put 2 zeros in. And now the positive tests are overwhelmingly more accurate than false positives with a disease so rare. And unfortunately, you just can't do something with swabs and PCRs that's 100 times more accurate than the tests we have. So the limitations on the testing accuracy mean that it doesn't do much for very rare diseases. The numbers for all of Oregon are down here also. So that's in our spreadsheet of stuff. Okay, so avoiding anything about what this actually means in your life or politics, questions about this stuff.
So according to what you just did there, can you explain to us how Douglas County as of 2 days ago is at extreme risk based on how the testing is so low here?
Because if the testing isn't accurate, that doesn't mean there's no risk. Those aren't related. And a lot of what drives public policy is hospital beds, because once you start running out of hospital beds, people start dying like crazy. And that's about all I'll say in a math class. So if you want to set good public policy, the hospital bed issue matters much more than how accurate your testing is. So watch the hospitals, don't watch the drive-by testing. Okay, this bit we skipped over is all about this, that if you have an absolute change or a relative change, we'll talk about them in just a few minutes on Wednesday. It's not that hard. If something is very rare, then the two ways of measuring change, subtraction or percent change, are going to give you drastically different answers. So we'll have a heads up about that. But pretty much we're done. You now have seen all of the Math 105 topics. It is just practice and homework and review from here. So congratulations. Yay. I will do my best in the next couple days to get the homeworks fixed up. Remember that we need to get a new 8B, and I need to make a 9B also. And I will also try and get your practice final, because some of you that have done 8B, which is now 9A, already are ready to start taking practice finals. One other thing I want to do also while I'm chatting and saying goodbye, put something in chat if you want study sessions. Then I'll know what to put in emails. So holler out to everybody, but I'll keep talking. What I want to do Wednesday also is have one person that has not done a good job of keeping track of their achievements. And one reason that we do the oral exam with the final is that besides talking about your final exam problems, we'll go through your achievement list. And most people have a bunch of them that they have actually done. They just haven't bothered to check them off yet. and we'll catch all those so they don't slip through the cracks. So if someone wants to be my demonstration helper, I'll make up a fake code name for you. Just copy your current information, and we'll spend just a few minutes going through your list of stars and say, oh, I have that one. Oh, I have that one. And we'll see how easy it is to get 10 more stars than you had if we actually go through it together.
You can do me. I can be your test little subject for that.
You might be on top of things enough. I'm not sure you're the best candidate for this.
I'm not sure if I'll make it to Wednesday's class. I'm having surgery on Thursday, so I have some preparation to do.
Okay.
But if I don't have to be there, you can use mine as an example.
You're also pretty caught up, I think. You've been good. I want someone that's been just ignoring achievements.
Oh, okay.
So that you can see dramatically that, yeah, if you were just sort of doing class, not caring about achievements, you've probably checked off a lot.
Yeah.
So if you want to volunteer, let me know. Otherwise, I will just pick an appropriate person and we'll make something up.
I think I want to volunteer.
Okay. So I think that will be reassuring, not only for Cassie, but for other people to say that, yes, I get a bunch of stuff checked off. This could have been me. Okay, that's all I have for today. Thank you a lot. If you have done all of homeworks 8A and B, then you sort of are waiting for me to get ahead of you. If you haven't, then you could either try the 8B, which is now 9A, or you could just wait until I get an easier thing to fill in the in-between spot as we go from one to another. Okay, goodbye. Have a great
Hi, thank you.
I had a quick question for you, David.
Okay.
So I know that it's going to take you a while to get the new 8B and the 9B.